So up to this point, where's my cover? There we go. So, up to this point, when we write down dy dx, that's one way of representing taking the derivative of something. You have some function y, which is a function of x, and when you say dy dx, you say, okay, I'm finding the slope of the tangent line. I'm finding the instantaneous rate of change from a physics perspective. So that's what it represents. It represents the derivative of the function. But what we're going to do is we're going to kind of modify that a little bit. We've alluded to it previously, but instead of, well, let me go in here a little bit. So that's what it stands. It stands for the derivative of the function y at any point, some value of x. Okay. So it's not really dy divided by dx. It's the derivative. It's ddx of y. This ddx represents the derivative. Another way we've shown it is by putting a prime next to the function. So we have f prime of x, or we have y prime. But in this section, we actually are going to make it into dy divided by dx. So if you remember back when we talked about the limit definition for the slope, or the limit definition for the derivative, it was the limit as delta x goes to 0 of f of x plus delta x minus f of x divided by delta x. And another way of writing that is that it's the limit of delta y over delta x as delta x goes to 0. Okay, so this delta y over delta x is kind of like dy over dx. So what we can do is we can kind of write out that dy dx exactly is equal to the derivative of the function with respect to x. That's just saying that these are equivalent to each other. There's just different ways of writing the same thing. It's finding the slope of the tangent line. But if we actually define the dx as a small change in x, so for a small change in x dx, we can estimate the corresponding small change in y. We'll call that dy. So at this point, what we're going to do is we're actually going to, instead of having a d dx of y, we're just going to have it over dy dx, kind of like delta y over delta x. So if we multiply both sides of this equation by dx, we come up with this expression, which says that if we know the slope of the function at some point in space, and we want to predict what the small change in y would be given a small change in x, we can use this relationship. So this now represents a small change in y and a small change in x. It doesn't represent, it's not exactly the derivative. And we need to use this when we talk about integrals. So that's the whole concept of differentials. So let's see what I said here. Near the point xy, a small change in y will result from a corresponding small change in x. Okay, that's dx and delta x are specified and are the same. Delta y is the actual change in the function between x and x plus delta x, where dy is an estimate of the function, assuming the function is approximately linear. That's on the next page. Between x and dx. We're going to show this in just a picture form. So we've got delta x and dx, which that's our independent variable, and we just specify them to be something small, and we're going to say that they're the same. Because if the function were linear, then delta y, wherever it is, delta y and dy are would be the same thing. But if the function is not linear, then they're going to be different, but dy is going to be a reasonably good approximation of what the actual change would be. So let's just look at this description on a curve. Well, let me just draw it if somebody's writing this down, so this will slow me down a little bit. So here's the x-axis, y-axis, here's the x-axis. Let's say here's the curve, so it's like a parabola. And what we do is we're talking about some x value and the corresponding y value. So we specify our starting point basically. We're starting it here at some value of x, and we know the function, so we know the value of y. And then we specify a small increment in x, which we'll call delta x. So this coordinate is x plus delta x. And the distance between these 2 points is delta x. And it's also dx. Okay, those in this case are the same. Now, if I take the slope of the tangent line at this point, so let me draw a line in, and I go from there at the new value of x. Here, if I go to this curve, which is the straight line, that is going to be equal to, well, actually what's going to happen is this little increment here is going to be dy, because that's assuming that it's linear between here and here, which is not exactly. If I extend this line a little bit further so that it goes to the function, and I go over here, this right here is going to be f of x plus delta x. It's going to be the actual value of the function. What I'm doing here is I'm approximating what the next value would be, assuming it's linear. Okay, so you get the small error. So what we're saying here is delta x and dx and delta x are specified under the same. Okay, delta y is the actual change in y, so that's the change from the initial value of y to the final value of y using the actual values on the curve. And dy is an estimate of the function, so it's right here, so it's slightly under predicting it, assuming that going from here to here it's linear and it has the slope of the tangent, slope of the derivative of that point. Okay, so that's the whole concept here. So what we're going to do here is we're just going to show the difference between delta dy and delta y. So we're given the function, kind of like the one that I just sketched. It's a parabola. Delta x and dx are the same. It's a small value, 0.1. And what they're asking us to do is two things. They're asking us to find is what is the value of the function at 2 plus 0.1, which is the value of the function at 2.1. So that's something. And delta y will be equal to the value of the function at 2.1 minus the value of the function at 2. That's the actual change. Dy is going to be equal to the derivative at 2 times dx. So let's do it. So f of 2.1, get the calculator out. So it's just 2.1 squared. So f of 2.1 squared. 2.1 squared is 4.41. Okay, and therefore delta y is 4.41 minus 4, because f of 2 is just 2 squared, which is 4. So you get delta y is 0.41. Now dy is just going to be equal to the derivative at 2. So we have to calculate the derivative. So y prime would be equal to 2y. So y prime at x equals 2, and that's not 2y, it's 2x. So the derivative at x equals 2 is just going to be equal to y prime at x equals 2 is going to be equal to 2 times 2, which is 4. So dy is going to be f prime of 2 times dx, which is 0.1, which is 0.4. So you can see the two values. The actual change in y is 0.41. The approximate change in y, dy, is 0.4. So they're pretty close to each other. I mean, they're within 1 out of 40, which is 0.25%. So it's a pretty good approximation. So let me just delete this page because I think there might be another problem in the next page. So same kind of deal here. What you're going to do, I'm going to let you do it, is you're going to evaluate the function at, so you'll evaluate the function at pi over 4. That'll give you something. You evaluate the function at pi over 4 plus 0.05. Okay, and then delta y is going to be the value of the function at x plus delta x. So you'll take that value and subtract the value of the function at the original thing. And then you'll calculate the derivative. F prime of x is going to be the cosine of x. So then you evaluate f prime at pi over 4, and then you calculate dy is going to be equal to the value of the derivative at the initial value of x times dx, which is 0.05. And you'll compare that number with that number and see what they are. So go ahead and do that. Make sure you change your calculator to radians. And you'll find out that the smaller that dx and delta x is, the closer dy and delta y will be, because as we've seen previously, as you zoom in on any curve, as you get a smaller increment, it approaches a linear, it approaches looking linear. So by the way, the homework I assigned yesterday, I don't know if I said it was due after the test. You don't have to. So just worry about finishing up homework through section 3.7 by Monday and studying for the test, which I guess I need to post the review, which I haven't done yet. Okay, let's see what we get here. Make sure my calculator's in radians. Okay. So the value of pi over f of pi over 4 is the square root of 2 over 2, which is 0.7071. If you add 0.05 to pi over 4, and then you take the sine of it, you get 0.7416. The difference between those two is 0.0345, so that's delta y. Then you take the derivative of the function, plug in pi over 4, which is cosine of pi over 4 is 0.7071, again, square root of 2 over 2. And then you multiply that derivative, 0.707 times 0.05, and you get 0.0354. So they're pretty close again. Okay, so I'm going to say less this time. So I've given you the function. Here's the method. Go ahead and figure out what delta y and dy will be starting at x equals 2 and then incrementing to 2.2, I guess is the... So has basketball practice started yet?
They've been having open gyms.
Yeah, that old open gym facade.
I run cross country.
Oh, did you run cross country? Okay. Yeah, I remember open gym. They did open gym when I was in high school. The thing I remember about open gym for a basketball was behind the school there was a orchard. It was in Winchester, and it was a orchard on a hill. So we would do these sprints up the hill, down the hill, up the hill, down the hill, which I guess really is not open gym because we weren't in the gym. But and I remember, and it was in September, October time, and I remember those apples tasting so good because we used to take the apples. I don't know if that was allowed or not, but that golden delicious juice. Running down my chin. Just wondering who's crunching there. Xavier. Okay, that's what I got. So I get delta y is negative 0.0196 and dy is negative 0.179. I think I did that right. So we evaluate the function at 2, value at 2.2 because delta x and dx is 0.2. And that gives you that. And then I take the derivative. Don't forget to use the chain rule. So you cancel out the 2's, you get a negative x, and you move that to the denominator. And you plug in negative 2 divided by the square root of 5, and you get that. And then dy is f prime of 2 times dx, and you get that. Okay. Yeah. This question is how many more do I want to do? I'm getting tired of doing them. So how does everybody feel about that? Does that kind of make sense? That's pretty much, this problem, I think there's one like this for homework. You basically, you evaluate the function at 2, and then you'd evaluate the function at 1.99 and 1.9, and you'd calculate what this is the, so that's the value of the function, and that is the tangent line approximation. So t of x just means that you're using the dy is equal to f prime of 2 times dx. And so these would be basically your, you take your original value of x and your delta y, and you would add that to get your actual, well, let's just work this one out. We'll skip the previous one. We'll go ahead and do this, and then we're almost finished with this section. So what you would do is evaluate the function at 1.9, evaluate the function at 1.99, evaluate the function at 2.01, and evaluate the function at 2.1. So you guys can help me out on this one. So somebody over here do 1.9, somebody in here do 1.99, somebody I'll do 2, and then somebody there do 2.01, and somebody over in that area do 2.1. So just evaluate the function, which is here, and I'll do it at 2, and then you can tell me what it is, and we'll fill out the table. So 6, for me, it's just 6 divided by 2 squared. For the rest of you, it'll be 6 divided by 2.1 or 2.01. So the value of the function here I get is 1.5. So anybody over there got one for 1.9? 1.66. Okay, how about 1.52? It's probably going to be 1.48. Yeah. I figured out that because it was 2/10 this way, 200ths this way and 200ths that way. Okay, Jacob. 1.36. Okay, so that's the value of the function. Now to do this part, if you take the derivative, which will be, well, let's rewrite the function, 6 times x to the minus 2. So that's going to be negative 12 times x to the minus 3 power, because you take the exponent, multiply by 6, which is negative 12. That's the same as negative 12 over x cubed. And if I evaluate the derivative at 2, I'll get negative 12 over 8, which is going to be negative 1.5 or 3/2. So that's the slope. So if you use this point slope form in the linear equation, you have y minus 1.5, that's the y value, times negative 3/2 times x minus x1, which is 2. So let's go ahead and multiply this out, and I've got fractions and decimals, so let's change to decimals. So this is going to be negative 1.5 x, and then we have positive 3 the 2's cancel out. And then if we add 1.5 to both sides, you get y equals negative 1.5x plus 4.5. So that's the tangent line approximation, assuming that you're using the tangent at 2, x equals 2, y equals 1.5. So now you can plug in these values again, so the same people can do, or the same grouping of people. I'm going to do at x equals 2, and I should get 1.5. So if I take negative 1.5 times 2 plus 4.5, that's negative 3 plus 4.5, which is 1.5. So they're exactly the same here because they're the same point. We used that point to make the linear equation. So what is the tangent line approximation number here, 1.9? Anybody? 1.65. And anybody over here? So plug in 1.52 into this equation. It's probably going to be not 1.52, 1.99. It's probably going to be 1.52, but somebody can. 1.515, okay. And this one is 1.48, and this one is 1.35. Yeah, okay. Thank you for making my life easier. So what you can see is that as in this case dy or dx or delta x is negative 0.01. Here it's positive 0.01. They're pretty close. As you go further away from where you did the calculation of the slope, the linear approximation is not quite as good, but it's still pretty darn good. So this, if I took this number minus that number, that would be delta y, actually the other way around. No, it'd be delta. So it would be 0.016 here. Dy would be 0.015. So it's just another way of doing the same calculation, but coming up with a equation for the tangent line and then using that to calculate these, because they do the same thing. They're assuming a linear change between one point and another instead of a nonlinear change. Okay. You can also use this stuff for error propagation. This is so this is problem 29 in your book. And the way you do it is you look at so in physics, you know, we had significant figures, and we're assuming that it's some value. Significant figures is kind of like plus. If you have one significant figure, it'd be like plus or minus 0.05, because 0.1 would be 1 decimal point. So you can kind of relate significant figures to how accurate the value is for the measurement. In this case, they're saying that the error in measurement for the length is plus or minus a quarter of an inch. The question is, how much error do you have in calculating area, which is not just length, it's length squared. So the way you do that is the way you handle or try to use differentials is you would take the length, or the radius in this case, I guess, the radius, which is a length. The length is going to be equal to 1.4. I guess that's 1.4, not. And then you'd have plus or minus 0.25. And so this is kind of like some value. It would be, this part would be kind of like a differential amount. It's a small value compared to the total value. Actually, it's fairly big error, so that's why I was trying to figure if that was 14 or 1.4. I think it's 14. Otherwise, it's not a very accurate answer. Okay, so you assume that it's 14 plus or minus 0.25. And so when you take, so this is kind of like, how do I want to do this? it's kind of like r plus dr, plus or minus dr. So you've got the value plus or minus this error. So when you calculate the area, what you have is some value of radius, the nominal value of radius, plus or minus dr times r plus or minus dr times pi. Pi is just a constant. So you can think of it as pi times 14 plus or minus 0.25 times 14 plus or minus 0.25. And then you could try to do this kind of like FOIL with the plus or minuses. So you'd end up with pi times 14 squared, and then you'd have 4 plus 14, this 14 times plus or minus 0.25, and then you'd have the inner, which would be another 14 times plus or minus 0.25, and then you'd have plus or minus 0.25 times plus or minus 0.25. You typically ignore that part. So when you multiply the errors together, it's so small that you don't really know it's insignificant. So then what you would do is you would take 14 times 0.25, and so that's this part here, you would get plus or minus 3.5, and this part you would get plus or minus 3.5, and this goes to 0, or it's insignificant. So you'd have pi times 14 squared. 14 squared is 196 plus or minus 7. So I add these two together. So your area value is going to be, average area value is just the nominal values multiplied together, but the error part is not just 0.25, it gets multiplied by 14 and it gets multiplied by it twice, so you end up with double the amount. And so that would give you an idea of how you would estimate the error in the area calculation based on the area of the original length measurements. So that's kind of, it's sort of a stretch as far as differentials are concerned, so I'm just pointing that out. What does it say? Okay, I think this is the last thing I want to talk about. Oh, because we're going to talk differential form of the equations. Okay. Okay, now there's let me read this. Okay, yeah. So this is kind of like the chain rule. You know, when you look at u prime of x, u prime of x is, you just take the derivative of it. So let me explain that. No. We kind of used it when we were talking about implicit differentiation. That seems so long ago, doesn't it? You know, when you use the chain rule, you had u prime of x equals something. You had f prime of u, and then you multiplied that by u prime of x to get the chain rule. It'll turn out later on that, so let me just define u of x as something. So let's say u of x is x squared. And so if I take the derivative of this with respect to so if I take the derivative of u with respect to x, I get 2x. And if I now make these into differentials instead of just calling u prime of x, I can say du is equal to 2x times dx. This is what's called the differential form of the original function. So it basically is the derivative of the function, but change the u prime of x instead of just being u prime of x, make it into du dx, and then say that we can treat those as a ratio of du divided by dx instead of the derivative of u with respect to x, and then multiply both sides by dx. So what this is saying, small change in u is going to equal 2x times a small change in x. So that's what, when we refer to differential forms of an equation, is you just take the derivative like you normally do and multiply by dx. I'm going to skip over this part for right now. We'll talk about it when we need to talk about it. So let's just look at these equations. What is the differential form of these equations? Well, this is actually, so what's the differential form of this equation? Well, what you do is you just take the normal derivative. So you'd say y prime is equal to 3 times the exponent times x to the exponent with 1 subtracted. So you get that. You get 2/3 x to the minus 2/3. And then you can simplify it. So you'd get 2x to the minus 1/3. That's equal to y prime. That's equal to 2 divided by x to the positive 1/3. And to make it into the differential form, all we do is we take y prime and we make it into dy dx. And then we multiply both sides by dx. So that, sorry, should have been, I wrote that wrong. Why did I do that? Okay, so that, all I'm doing here is changing y prime into dy dx. And then I have my function, and so then I multiply both sides by dx, and so I get 2 divided by x to the 1/3 times dx. So that's the differential form of the original function. It's basically the derivative, then multiplied by dx, so that you get dy is equal to 2 divided by x to the 1/3 power, which would be the cube root, times dx. So let's just do one more. So let's say we have this function, and they say, what is the differential form of that function? Well, all you have to do is you just take the derivative, y prime, which is going to be 1/2 times 9 minus x squared to the minus 1/2 power times negative 2x. And then we clean it up a little bit. So you get y prime is equal to negative x divided by the square root of 9 minus x squared. We did that just a minute ago. So the differential form is you change y prime into dy dx like that, and then multiply both sides by dx. So you get negative x divided by the square root of 9 minus x squared times dx. So that's the differential form of the equation. Okay, so it's not too difficult. It's just taking normal derivatives and then multiplying changing this into y prime into dy dx, multiply both sides dx so that you get dy isolated on the left-hand side, and you get the derivative times dx on the right-hand side. Okay, so that's, we will, when we do integration, we'll deal with things that look like that in differential form. So we just need to introduce what that means. That's what it means. So there's not many problems. It's like I said, it's mostly just the purpose of that section is to introduce differentials, how you get differentials, how you get the differential form of something. But that won't be, it won't be on any tests or anything like that. We just need that for the next part. So now we move to chapter 4. Which is integration. So we're gonna do something similar to what we did when we talked about derivatives. We're going to introduce the general concept of derivatives. We're going to do some really in-depth calculations like we did when we used the limit definition for the derivative. And we're going to but then we're going to kind of like, oh, I see something. You know, you make some observation like, hey, there's these formulas that I can come up with for derivatives, and I'll just use the formulas. I don't have to use, you know, f prime of x is the limit as delta x goes to 0 of f of x plus delta x minus f of x over delta x. I don't have to, you know, do all that kind of stuff. So, but actually before that, that's actually in the next section. The first thing we're going to do is just talk about this concept of antiderivatives. So it's kind of like, you know, you have addition, and the opposite of addition is subtraction. You have multiplication, the opposite of multiplication is division. You talked about inverse functions, and you know, this in math you have something and you have the reciprocal of something. You know, like if there's 6, then you have 6 and a 6, and you multiply those together and you get 1. So there's always this kind of yin yang thing. And so we've defined derivatives. And so if we have, so we're going to call something called the antiderivative, which basically means you're going the opposite direction. So as a kind of a concept here is if I said, you know, f of x equals x squared, so that's the original function. If I take the derivative of that, I get 2x. So this is the derivative, which we had the limit definition to do that. If I said, what is the antiderivative of 2x, question mark, you'd say it is x squared, right? So the way you can kind of ask this question is, what is the function whose derivative is 2x? And you'd say, oh, it's x squared, because if I take the derivative x squared, I get 2x. So let's think of another one. Let's say, you know, let's say f of x equals the sine of x. So from derivative land here, the derivative of cosine of x, sine of x is cosine of x. So then I'd say, what is the antiderivative of cosine x? And the answer would be the sine of x, because the function whose derivative is the cosine of x is the sine of x. A lot of is's there, but so that's the basic idea of antiderivatives. We're just going to say it's the thing that the function whose derivative is the what I'm trying to find the antiderivative of. So all the rules that we had, all the rules that we came up with in chapter 2 for derivatives, we also have the rules for going the other direction. So we could, you know, for example, here's another one. What is the antiderivative of x to the n? We know what the derivative of x to the n is. It's n times x to the n minus 1. So that is the formula that we know how to use because we've done it so much. Well, if you think about it, it turns out the antiderivative of x to the n is x to the n plus 1 divided by n plus 1. Okay, so if I said over here here n equals, actually here n equals 1. So the antiderivative of 2x is going to, which is x to the first power. So the antiderivative of x to the first power is x to the second power divided by 2. So using this, and then using this formula, I would get back to that. So this is kind of like the general antiderivative formula that applies to the one that we've used multiple times. So just as an example, if I said, what is the antiderivative of the following functions? X squared, x cubed, x to the fourth, x to the fifth. Well, the answers are, you add 1 to the exponent and divide by the new exponent. You add 1 to the exponent, divide by the new exponent. You add 1 to the exponent, divide by the new exponent. You add 1 to the exponent, divide by the new exponent. So these are all the antiderivatives of those. And so this is the anti part. Now if I now take the derivative, go the other direction. So this is the antiderivative. Now I'm going back. If I take the derivative of that, I should be back to where I started. So what you would get is 3x squared divided by 3, which is x squared. Here you would get 4x cubed divided by 4, which is equal to x cubed. And this one is 5x to the fifth divided by 5, which is x, pardon me, I went the wrong direction. Let's try it again. It's going to be 5x to the fourth divided by 5, which is x to the fourth. And going this way, you get 6x to the fifth divided by 6, which you get x to the fifth. And you can see that, these are the same. So when you take a function and you take the antiderivative of it, and then you take the derivative of the antiderivative, you're back to where you started. So it's kind of, if you add something and then you subtract the same thing, you get back to your original number. And you can apply that with this whole concept of derivatives and antiderivatives as well. So section 1 is basically using, let me just, and we'll come back to this on Thursday, but I'm just kind of introduce you some stuff here. I'm trying to find my table. Yeah, here it is. So there are tables in your book, and now I've used the word antiderivative, but another word that we use for taking the antiderivative is called integration. So here are the derivative formulas that were in chapter 2. The derivative of x, a constant times x is just a constant. So the derivative of 3x is 3. This is the constant multiplier rule. So if you take the derivative of a constant times a function, it's just the constant times the derivative of the function. And this is just the addition rule. And so these are all derivative rules that we had in chapter 2, and these are the corresponding antiderivative or integration rules. So this is the power rule, which corresponds to the derivative of the power. Here's the antiderivative of the power, and you can see that the antiderivative or integral of x to the n dx, and we'll come back to this dx thing here in a second, but is x to the n plus 1 over n plus 1. That's the formula that I was just talking about. So for each derivative formula, there's a corresponding antiderivative or integral formula. And notice that how this is set up. This looks kind of like the differential form of the equation. So that's one reason we introduced differentials, is because when we do the antiderivative, we include this little dx thing at the end. We don't just say antiderivative of x to the n. We do this integral, this scroll thing. We say the function that we want to take the antiderivative of, and we put this little dx. And what the dx is telling us here is that we're integrating this thing with respect to x. And because we're in single variable calculus, that's all we only integrate with respect to the same variable that we're dealing with. Yes?
I see that it says for n does not equal -1.
Yes, that is a special case. It's kind of like with the x to the n, when you take the derivative, it didn't work for n equals 0. So this formula doesn't work for -1, and that special case we'll find out later is the natural log. Okay, that it works for every value of x except for -1, and we will deal with that in chapter 5. Okay, so that's a basic concept here. So let me just review that. Right now we're just talking about this operation called the antiderivative. And the antiderivative is the opposite of the derivative. So the formulas that we had for derivatives, we have corresponding antiderivative formulas. If you take the antiderivative of something and then take the derivative of it, you're back to where you started. Okay, so we'll talk more about this in a little slowed down version, but that was my kind of quick introduction of where we're going. Ultimately, we'll find out the integral also represents the area underneath a curve, which we've talked about in physics. So there's actually two interpretations of this operation. One is antiderivative and one is area. And the fundamental theorem of calculus shows the equivalency of those two things.